This is going to be Chapter 9, Part 4. We've talked about and defined enthalpy, and now we're going to use enthalpy to solve more problems using Hess's law. Now, Hess's law relies on the fact that enthalpy is a state function. A state function is a variable whose value depends only upon the current state, not how you got to the current state. So a really general example I like to start off with is, let's say we're all going to go hiking and we're going to go up this mountain, and you folks with your young knees, right, you're going to go straight up the mountain. I, on the other hand, am going to take a more meandering, less steep path, and I'll meet you guys up there, right? If we looked at, say, the number of steps that we took, that's a path function. That very much depends on which path you took, right? But if we look at change in elevation, right, it doesn't matter if you went straight up or you went meandering up with me. We all started at the bottom, we ended at the summit. Our change in elevation would be a state function. If you think about this in terms of a road trip, right? Let's say one group takes their car on the highway and goes straight from, let's say, Waco to Dallas, right? Just go straight up 35. And another group goes off the beaten path and takes a meandering trail and then also winds up in Dallas, right? The overall change in distance and location is going to be the same, but the miles driven, the gas used, those are all going to depend on the path. Okay, so how does this apply to a chemical reaction? Well, Hess's law tells us that an enthalpy change for any process is independent of the way that process was carried out. So when we look at this graph, right, if we go from starting materials to products, and let's say it somehow just goes straight there, right, this is the change in enthalpy that we are interested in. But what order the bonds broke and what order they formed, right, it can lead to different intermediates. Maybe you broke it all the way down to the elements, came back up to the products. It doesn't matter which path you took, the overall delta H is going to be the same. So if you added up delta HAI and delta HAF, that would be equivalent to delta HBI and delta HBF, because whichever path you took, you have the same start and the same finish. So this allows us to calculate delta H's of reactions based on, right, intermediate steps. So let's start off with a simple problem. Well, okay, we are going to solve this sulfur and oxygen problem in just a moment. You can see in this example the combustion of methane, right? Whether methane and oxygen react and immediately form CO2 and water, or if there's an intermediate step where you make CO, carbon monoxide, and then the carbon monoxide reacts to form CO2 and water, right? The overall delta H from starting material to products is going to be the same, right? Whether you went straight there or you took a more meandering path. In this instance, with this sulfur trioxide compound, we're looking for delta H of this reaction. But we are given information on steps in a reaction. We're going to have to figure out how to add these together to get the desired reaction. So we're going to have to do some manipulations. Now, I focus on the starting materials or products that are only found in one of the reactions. So for instance, oxygen is in both of these reactions, so I would not focus on that. Let's start with sulfur. We want sulfur, 1 mole of it, to be in the starting material side. So we're going to write down that first reaction. It has 1 mole of sulfur reacting with O2, giving us sulfur dioxide. And since we didn't change anything, we're not going to change delta H. It's going to be negative 296.8 kilojoules. Now, in the next part, we see sulfur trioxide right here, but in the reaction that we are focused on, we want there to be 1 mole of sulfur trioxide. In the data that we're given, we have 2 moles. So we need to manipulate that first before we add them together. If I'm going to divide this by 2, I have to divide the whole equation by 2. That's going to wind up giving me SO2 gas plus half a mole of O2 gas, yielding 1 mole of sulfur trioxide. Now, since I divided everything in the stoichiometry by 2, I also have to divide the delta H by 2. So that's going to be negative 98.5 kilojoules. Make sure everything is balanced. Then we're going to add our equations together. I'm going to do this kind of in a longer fashion the first time. When you add reactions together, you're going to take all of the starting materials, so sulfur plus O2 plus SO2 plus half a mole of O2 yields a mole of SO2 gas and SO3 gas. Now, we're going to clean this up. Anything that is on both sides unchanged can be left out, right? Because technically sulfur dioxide is unchanged from beginning to end. It's kind of like the spectator ions. We're going to cancel that out. Anything that shows up more than once on one side, we can go ahead and combine. So really, this is sulfur plus a mole and a half, or 3/2 of O2, yielding 1 mole of SO3 gas. And that's exactly the equation we were looking for. So since we've added these up, we can also just add up delta H. So negative 296.8 plus negative 98.5 gives us negative 395.3 kilojoules. And this will be delta H of this reaction, because it doesn't matter the path, right? It doesn't matter which set of intermediate steps, as long as we wind up with the same initial start and the same final place, the final product, then we can calculate delta H because it is a state function. Now we're going to do another practice problem with, we'll come back to that, with carbon disulfide, 3 moles of oxygen forming CO2 and 2 moles of SO2. Now, we have 3 equations. What I would recommend is that you do one at a time. I mean, not one. You add 2 at a time. So I'm going to start off with CS2. Now, where can I find CS2? It's in the 3rd equation, and it's on the product side. So I'm going to have to flip it. I want the CS2 to be on the starting material side, and then the carbon and the sulfur will be on the product side. Now, since I flipped it, that means I have to change the sign. Positive 87.9 becomes negative 87.9 kilojoules. I didn't multiply or divide, so it's just a change in the sign. So what I chose next, because I'm not going to use oxygen, it shows up too many places, I'm going to look at CO2. Now, in this second equation, CO2 is in the right spot. It is already 1 mole, so I just have to write down carbon plus O2, yielding CO2, and delta H, negative 393.5. Now, I'm going to add those together before I keep moving on, so I can see what I need. I see that there's 1 mole of carbon on the product and the starting material side, so I can cancel that out. So I'm going to wind up with carbon disulfide plus a mole of oxygen, yielding 2 moles of sulfur and CO2. Since I added that equation, now I'm going to add the delta H That's going to be negative 481.4. So I have my CS2, I have my CO2. Oxygen's not quite there, but that one's still going to be more difficult. Next, I'm going to look at sulfur dioxide. That second equation has sulfur dioxide in it. It's in the right place, but we need 2 moles. So now we're going to multiply everything by 2. So I'm going to have 2 moles of sulfur plus 2 moles of oxygen, yielding 2 moles of sulfur dioxide. Since I multiplied everything by 2, I have to multiply delta H by 2. That's going to be negative 593.6. Now let's add those together. You have 2 moles of sulfur on each side, so those will cancel out. You have 1 mole of oxygen and 2 moles of oxygen, so we're going to combine those. All right, so we have our carbon disulfide, 3 moles of oxygen, yielding CO2, and 2 moles of SO2. All right, so that matches perfectly with what we were trying to solve. So to finish the problem, we just need to solve for delta H. Oh, we did not want to do that. There we go. Okay. Delta H is now, we are going to see, be equivalent to negative 1,075 kilojoules. All right, these are fun little puzzles, but you definitely need to practice. Remember, whatever you do to part of the equation, you have to do to the whole equation. If you flip it, change the sign. If you multiply or divide, don't forget to do that to your delta H's. Following that same logic, all right, we can think about the overall delta H in terms of breaking every starting material down into the elements and then forming the products from the elements. All right? This equation is that you see right here is based on Hess's law. So it's saying that if we take the energy of formation of our products, so the energy that it takes to form a mole of our products from the elements, and we subtract the energy of formation, right? So that's going to be how much energy it took to break the reactants into the elements. We can also find delta H. Now, this is going to require us to use tabulated data, right? So we're using standard molar enthalpies of formation, right? Delta HF. This comes in a table. It's not on the slideshow, and but what I will tell you is this would have to be given to you in the problem. You are not supposed to know these offhand. In your homework, there's a link, I'm sure, to tabulated data. So what I'm going to show you is let's write down our balanced equation, because that's going to be important. VI is going to take into account the stoichiometric coefficients. 1 mole of C3H8 reacts with 5 moles of oxygen to give us 3 moles of CO2 gas and 4 moles of H2O liquid. It is important to recognize the states because, for instance, when you go to look up HF for water, there's going to be one for a liquid and a gas. So it's important to know which one you're looking for. Now, when I go to the table, I find delta HF in kilojoules per mole for each of my materials. For propane, it's negative 103.8. For CO2, it's negative 393.5. For liquid water, it's negative 285.8. Negative 285.8. Now you notice I skipped oxygen. Well, O2 in the gaseous state is the elemental form. So there is no heat of formation there. It's already in its elemental form. So oftentimes you won't even see this on a table. If you're looking at an element in its elemental standard form, HF is going to be 0. Now that we have this data, it's really just plugging in. So we're going to start off with products, right? And it's the sum of the heats of formation of the products. So for CO2, it's going to be 3 times negative 393.5, right? Because HF is always based on 1 mole. And to that, we're going to add 4 times negative 285.8 for the water. Then we're going to subtract the reactants, I'm so sorry. That's going to be 1 times negative 103.8. I leave out oxygen because if you add 0 plus 5, 0 times 5, you're just adding 0. When we solve this, and you want to be careful with parentheses, we're going to find that the overall delta H, the overall enthalpy change for combustion of 1 mole of propane is negative 2,219 kilojoules. And it's as simple as that. There will be a practice set on eCampus for Hess's law problems. I encourage you to do a few of those. They're not hard, but it helps to do some practice, get that into muscle memory. The final thing that we're going to cover is just to remind ourselves that a thermochemical equation is a balanced equation. And so there is certain stoichiometry certain stoichiometry problems that we may be able to do. So if we look at this example problem, an engine generates 15.7 grams of nitric oxide, right? So the NO gas. During this test, how much heat was absorbed? So you notice delta H is positive. That means this reaction requires heat. It's endothermic. We want to know how much was absorbed by producing this amount of NO, right? 180.5 is for 2 moles of NO. So we have to convert 15.7 grams of NO to kilojoules, right? So we know that if we're looking at stoichiometric ratios, it's in moles. So we need to convert grams to moles first. There are 30 grams of NO in every mole of NO. And then the stoichiometric relationship to energy is 2 moles of NO require 180.5 kilojoules of energy. So if we solve, right, moles of NO and grams of NO cancel out, we find that the amount of energy needed is 40